The first definition of acids and bases we'll be looking at is the Arrhenius definition. This is named after a Swedish chemist who was named Arrhenius. So there's going to be, I think, 3 different definitions. I am not going to ask you what is the Arrhenius definition as opposed to one of the other definitions. I don't really care if you remember the name of the definition. I only care if you're able to apply that definition. So in this definition, an acid is a substance that produces hydrogen ions in aqueous solution. A base is something that produces hydroxide ions in solution. So if we look at HCl, we've learned in general chemistry, well, Chem 1A, to recognize that as an acid because it starts with an H. Its name is hydrochloric acid, so that's a big clue as well. That's an acid because when it dissolves in water, it produces hydrogen ions. Hydrogen and chlorine are both nonmetal elements, and so this is a covalent compound. It's molecular, it's not ionic, but it ionizes, it forms ions in water, and so it forms hydrogen ions and chloride ions. Those hydrogen ions are very reactive, and they will bond to water, forming hydronium ions. So the hydronium ion is H3O+. There are other similar things that exist, but we don't need to pay attention to them. So here's a little illustration. Here we've got the hydrogen ion, and we've got a water molecule. Let's think about what is a hydrogen ion. A hydrogen atom has how many protons? 1. And how many electrons? 1. So when it becomes an ion, it loses its only electron, and what's left? A proton. Okay? So this isn't even close to being an atom anymore. Right? It's just a proton, a piece from a nucleus. Not very stable on its own. So this is going to react with anything it can. And so in an aqueous solution, there's water everywhere. And so this guy has no electrons, and here's water, and this oxygen has 2 lone pairs. So what this oxygen very generously does is it shares one of its lone pairs with the hydrogen that has no electrons. And so it forms a bond in that way. Overall, this has a positive 1 charge. We will use H plus and H3O plus interchangeably. So I just want to warn you about that because sometimes it'll say H plus and sometimes it says H3O plus. The H plus I think of as being like a very tiny baby, a very, newborn baby. Do you see little babies out on the sidewalk by themselves? No, of course not. For one reason, they can't walk, right? How would they get out there? So this is like a baby, and you're never going to see it alone, right? So it's going to be riding or being carried by a water molecule. But if we use H3O plus in all of our equations, it makes the chemical equation, a little more complicated. And so we'll often use just H plus to simplify things, but H plus aqueous, we understand to mean that the baby is not out there all by itself. It's riding on a water molecule, right? The baby has someone with it carrying it. Okay, the definition of the base produces sodium hydroxide ions in solution. So common base is sodium hydroxide. This is an ionic compound, and so when you dissolve it in water, it dissociates, meaning the ions come apart. So we've got sodium ions and hydroxide ions, and these hydroxide ions are what make it a base. So acids and bases will combine together to neutralize each other. So here we have a hydrogen ion from the acid, which we understand is not actually just by itself, it's being held by a water molecule. And here we have the hydroxide ion from the base. This hydrogen ion can leave the water molecule that it was with and go with the hydroxide ion and together these will form a neutral water molecule. So this is the net ionic equation for a lot of acid-base reactions. Any questions yet? A second definition is called the Bronsted-Lowry definition. This applies in a wider area, and this is focused on the transfer of ions. So we're not talking about, well, it produces hydrogen ions in aqueous solution, but it transfers hydrogen ions to something. What if you have a solution that is not aqueous? What if your substance is dissolved in methanol? Well, how can you define it as an acid or a base when the definition requires water, right? So this definition applies to things where water is not the solvent. The acid is the proton or H plus donor. We just talked about a hydrogen ion is just a proton, right? So the acid will donate a proton and the base will accept the proton, the hydrogen ion. So I think of the base as being like the babysitter, right? The acid is the parent. The acid has the hydrogen ion, the proton, and it's going to pass it off to someone else for a while, right? So the babysitter accepts the proton, the baby, and the acid passes it off. Donating babies doesn't sound quite right. So HCl is defined as an acid under this definition as well, because it donates a hydrogen ion to water. So HCl ionizes and it donates this hydrogen ion to the water molecule, resulting in H3O+. So this is really a combination of two equations that we looked at before. There we go. Yeah, so here we have the hydrogen chloride, or the hydrochloric acid, right, forms these two ions. And then a hydrogen ion will react with a water molecule to produce the hydronium ion. And so here, this is just the combination of those two chemical reactions. So this is very clearly describing what is happening to that hydrogen ion. It's not just going off in solution by itself. It's going from the HCl to the H2O. Any questions? Oops. Yeah, so the base is a proton acceptor. And so this applies better to bases such as NH3. If we just look at the chemical formula for NH3, it doesn't have hydroxide in it, right? And so you're like, well, how's that a base? All the bases, they're like metal hydroxides. They dissociate, and there's the hydroxide ions that are the base. Well, this is what happens with ammonia. Ammonia is a base because it will accept a proton from water. So we put ammonia in solution, dissolve it in water, and the water will donate a proton to the ammonia. That produces the ammonium ion and the hydroxide ion. Today in lab, we are going to be using aqueous ammonia. So on the bottle, it says ammonia, not NH3, so the reason that all of our stock bottles are labeled with the names instead of the chemical formulas is that the label maker doesn't do superscripts and subscripts, right? So we just write out the names. So it's labeled ammonia, aqueous. When you dissolve ammonia in water, it forms ammonium hydroxide. So it can also be called ammonium hydroxide. So in your lab manual, it refers to NH4OH, ammonium hydroxide. The bottle says ammonia. They are exactly the same thing. So acids and bases always occur together because the acid is the proton donor and the base is the proton acceptor. You can't have one without the other. Remember not acid base, that's what we're talking about right now. Oxidation reduction reactions, those involve the transfer of electrons, right? And so one thing loses electrons and those electrons go to something else that gains the electrons. You can't just lose electrons, it just doesn't happen. There's no bank where you can go and take out electrons. You have to get them from another substance. So if we look at this reaction with the acid here, there has to be a base as well. So this is donating a hydrogen ion. What is accepting the hydrogen ion? The H2O. So this is our acid, HCl, and water here is acting as a base. In the one above, NH3 is a base. It's accepting a hydrogen ion, a proton. Who's it getting it from? H2O. So here, water is acting as an acid. So if you have an acid, there will be a base. So we just saw that water acted as an acid in one situation and as a base in another situation. Substances like that are said to be amphoteric. And this prefix ampho is like amphibian. It's the same prefix. Amphibians live on the land and in the water, right? Both. So amphoteric substances can be acids or bases. They can do either depending on the situation. So let's look at this Bronsted-Lowry acid-base reaction from the previous slide where we had ammonia reacting with water to form ammonium ion and hydroxide ion. And we're just writing the equation backwards. This is an equilibrium, and so writing it backwards is very, very reasonable. If we look at our reactants now, one of them is transferring a hydrogen ion to the other. Who's losing the hydrogen ion? NH4. So NH4 is now the acid, and OH minus is the base because it's accepting the hydrogen ion. So the substance that was the base becomes an acid. So it's a little like, a game of hot potato or something where, does anybody even play that anymore? Do you know what that is? Hot potato? Hot potato, and you pass it around the circle. It's a little bit like a cakewalk or something, The music stops and whoever has it either wins or loses depending. So if the acid gives a proton to the base, now the base has the proton. The base could donate that to something else, right? That's an acid now. So in the process of accepting the proton, the base becomes an acid. And in the act of donating a proton, the acid becomes a base. Not confusing at all. We're just looking at who's got the hydrogen ion. So these form what we call conjugate acid-base pairs. So a conjugate acid is what you have after a base accepts a proton. A conjugate base is the acid after it has lost its proton. So what we refer to as a conjugate acid-base pair are two substances related to each other by the transfer of a proton. One has the proton, the other does not. So if we look at ammonia, if we add a hydrogen ion to ammonia, we get NH4+. This is the conjugate acid because it has the hydrogen ion. This is the base because it could accept the hydrogen ion. These are related to each other. The only difference is one has an H plus and one doesn't. We can look at water. If we take a hydrogen ion off of the water, we get hydroxide. So here, water can act as an acid by donating a proton. Then it becomes a base capable of accepting a proton. Any questions? Yeah.
So if it gains the proton, it's an acid.
The acid is the one that loses, and the base is the one that accepts. After the base accepts the proton, now it is an acid. Yeah, so it's the conjugate acid of the base.
So if it starts off as a base,
It becomes an acid. If it starts off as a base, it becomes an acid. If it starts off as an acid, it becomes a base. Because the difference between them is who's got the hydrogen ion. Yeah. Any other questions? It's kind of a weird idea. Okay, so this problem asks us to identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. Don't let Bronsted-Lowry in front of acid confuse you. It's not a trick. It's going to say that on exam questions. It might say, identify the Arrhenius acid, or identify the Bronsted-Lowry acid. And it's not because there's one of the other kind there that you're supposed to ignore. It's just the way the problem is asked. So you can just ignore that part. Just ignore that. Identify the acid and the base. So in this one, here we have two reactants, and a hydrogen ion is being transferred to form these two products. So what we want to figure out is, well, where did the hydrogen ion come from and where did it go? So this one has a neutral charge, and this one has a positive charge, right? This one has an extra hydrogen now that it didn't have before. So this one, in the process of this reaction, accepted a proton. So it is what? The base. So base and acid, acceptor and donor. That's why I like to think of bases as babysitters. Because what's a babysitter for? To sit with your baby, right? So the babysitter is there like, hey, I'll take care of the kid for you. So the acid passes it off to the babysitter. So this is the base. It's accepting the proton. Well, after it accepts the proton, what does it become? The conjugate acid. Because now it has a baby that it could hand off to somebody else. The babysitter could, get a babysitter. That's, kind of frowned upon by parents, but as long as the kid's okay. So where did that hydrogen ion come from? It came from the H2O. Right? Here we had H2O. Now we have OH minus. There's only one hydrogen. So this was the acid. It donated its hydrogen, and so it becomes the conjugate base. So H2O and OH minus are a conjugate acid-base pair. The reactants are labeled acid and base. The products are labeled conjugate. Okay, let's look at B. Which one of these is the acid? HNO3. There's two ways you could identify that one. It starts with an H. So from nomenclature, we learn to recognize this as an acid. But we can also look at what happens to this guy. Over here, it's lost its hydrogen ion. So if that's the acid, what's the base? H2O, the other one. So then H3O plus, what is that? Conjugate acid. I'm just gonna call it Ca. And NO3 would be what? The conjugate base. Does that make sense? We're just passing the hydrogen ion back and forth. So that kind of a question could be on the next exam. This kind of a question could be on the next exam. Which pair is not the conjugate acid-base pair? What we're looking for in a conjugate acid-base pair is one formula has an H plus that the other one doesn't. So if we look at this first one, what is the difference between these two formulas? An H plus. This one has the H plus, this one doesn't. Is that a conjugate acid-base pair? Yes, it is. How about this one? What's the difference between these two? An oxygen. This one has 4 oxygens, this one has 3 oxygens. Is that a conjugate acid-base pair? No, because we're looking at, we're looking at hydrogens, not oxygens. Is this an acid? Yeah. Is this an acid? Yes, they're both acids, right? But they're not a conjugate acid-base pair. How about the last one? Conjugate acid-base pair? Yeah. This has the hydrogen, this does not. You see how it works?